In the last video, we talked a little bit about the primary elements of solving limits algebraically. The first rule of which is sometimes called limit law number one, and it says the limit of a constant is equal to a constant regardless of where x is heading. Looking at an example, you can write your own explanation in the notes, but I'll go ahead and just write an example. Say I wanted to know what's the limit as x approaches 42 of 77 or something. Just throwing some random numbers in there. The point is that if we have a constant in there, aka there is no x, the limit is just equal to that value of the constant. Wherever we're heading does not matter, because x is not part of the expression to which our limit is evaluating, and therefore it will not change. Of course, you could look at the graph of 77 or try plugging in numbers, but there's nothing to plug in, right? So the limit will never change, and that's just a trick for evaluation. Now, another law which is not written on your notes, we'll just go ahead and call it law number 7. I actually don't remember if it's in our book or if it's represented somewhere specifically, but it's that the limit as x approaches a of x must always be equal to a. And that was the other idea I was trying to demonstrate in the first example, that if we have the function just x, the limit is always equal to the target or the value to which we're heading to in the limit. So again, if we're trying to look at an example of this, again, you can try to use your own words to look at an example, but say we just plug in, well, what's the limit as x approaches 42 of just x? Well, here, my whole point is if we have just x within our limit, we can just plug in 42, and therefore we will solve our limit algebraically without having to look at graphs or numbers. And a lot of these laws are kind of the building blocks of solving limits algebraically. Now, the other rules for solving limits, laws 2 through 6, are also important, and I wanted to show you guys how we can kind of use these in some of the following examples in the packet. But if we look at law number 3, the law number 3 says that if I'm taking the limit as x approaches a of f of x plus or minus g of x, that's going to be equal to the limit of the first function plus or minus the limit of the second function. And the plus or minus here I'm just using to say, well, this could either be a sum of two functions or the difference of two functions. This will work either way. And what you'll end up getting is, if our functions individually have limits, so the first function has a limit of L, you can just let L be, like in this previous example, we looked at x and 3 as our two separate functions. Then we considered what happened if we add them together. And the point we noticed was that, well, the limit of this one, imagine this is capital L here. Let me just write this so it's a little easier to keep track of the comparisons here. Imagine this is L, and this is m as the values of the destination of our limit, the evaluation of the limit. Then the sum function of both f plus g is just equal to L plus m. Assuming those individual functions have their own limits, if we try to add them together, the limit of the sum function will just be equal to the sum of the limits. And that's exactly what this is saying, is that if I have a limit encompassing two functions, I can just take the individualized limits, which of course will just be equal to their individual limits, either added or subtracted. You can also think about this sort of like the distributive property in algebra, where if I'm taking a limit of a sum, the limit will kind of distribute to each. It's not called the distributive property, but it's a similar structure where we can take the limit of each individually and solve them. And why that's helpful is, well, if we're dealing with a more complicated function, we can separate it to simpler components. And if we know the limits of the simpler components, we can use those to solve more difficult examples. The remaining limit laws all illustrate similar traits, which I'll leave it to you guys to think about why they make sense. But kind of a similar reason to why this makes sense is, well, if you're going to add them together, of course, the limits add, assuming the limits actually work in the first place. But what law number 4 says is that the limit of f times g is equal to the limit of f times the limit of g, aka we can just multiply the results of the limits together. Law number 5 is actually not quite right, because it says the limit of f of x divided by g of x is equal to limit of f divided by the limit of g L over m. And now this one, as we know, we're not allowed to divide by 0 in math, and this one specifically only works if m does not equal 0. Or another way we could say this is that g of x cannot be 0, because dividing by 0 in that that specific location could be problematic. And that's a note that, you know, if you go into your textbook, they'll go more into the details. But generally, the point is, if we have a division of two functions, we can separate the limit to them individually and solve those. However, there is one caveat here, and we'll address these in more examples. Actually, we've already seen a few, but we'll kind of look more into that soon. In law number 2, I skipped over intentionally because, well, it only makes sense because of law number 4, and it's actually the book just has them organized in a way that I would not organize them myself. That's okay though. It says that the limit of x as x approaches a of f of x to the nth power is equal to the limit of f of x to the nth power. So the difference in these two expressions is that on the left, it's saying the limit of the whole thing is equal to, well, now we can take the limit of just f, then raise it to the nth power after. So imagine there's a parentheses here. What this is saying is, you know, take the limit of the entire function to a particular power will be equal to the function to the nth power. So let's look at an example, because this one is not as obvious. So let's just say we're looking at the limit as x approaches 2 of x squared, kind of similar to the limit of just x by itself in the previous video. And the question is, well, what is this limit? Again, you could plug in numbers, you could graph it. There's various ways you could solve this, but doing it algebraically, if we use law number 2, what it says is that we can essentially put a parenthesis in here. We can take, well, what the limit as x approaches 2 of x squared. Instead of having the squared on the inside of the limit, I can move it outside the entire limit. And then the reason why that's helpful is, well, what it's saying is that actually the limit is just the limit of the inside to the nth power, or the limit, in this case, limit squared. And the reason why this is cool is, well, we know the limit as x approaches 2 of just x by law number 9, right? Because if I have just x, what happens is I'm just going to get a. I just plug in the value of the limit. So for x by itself, we know its limit is 2, so we're just going to get 2 squared, or 4, as the value of our limit in this instance. And similarly, this also works with cubes, 4th powers, 5th powers, actually any power, even fractional powers. It works for roots as well, which also not, you know, again, we don't want to get overly into the details of a lot of these things. But if you're wondering, okay, well, why does it make sense for the base case such as squaring or cubing? Well, it's predicated on law number 4. And you know, law number 4 is really predicated on law number 3. But basically what this is saying is, if I have a product, I can take the limit individually of the function. Well, imagine f and g were both the same function. Both of these were f's. Then I'd have f squared. And what that would say is the limit of f times the limit of f. And what that would give me is the limit of f quantity squared. So essentially, law number 4 proves the first part of law number 2. And similarly, taking other powers of n, including radicals and so forth, also hold true. So let me go ahead and wrap this video up, because I don't want to get overly into a lot of the details, but I want to, what is the point? Because this is where, you know, we're getting into a lot of algebra and things that honestly are not critically important, but what is important is these rules allow us to solve these limits using algebra, and there's some simple tactics to solving these, basically by plugging them in. And that's really the key takeaway, in my opinion. Let's wrap this video up, and in the next one we'll kind of talk about how we use the the limit laws to solve limits algebraically.